Welcome back to my YouTube channel. In this video, we will talk about skewness and its types and methods. How can we handle it? So let's start with skewness. So what is skewness? Skewness is a statistical measure that quantifies the asymmetry of the probability distribution of a dataset. In simpler terms, it tells you how much a dataset's distribution deviates from being symmetrical, that is, bell-shaped like a normal distribution. Skewness is an essential concept in statistics and data analysis because it can provide insights into the shape of your data distribution. Type of skewness. There are three types of skewness, that is positive skewness that you can call right skewed, and then there is negative skewed, that means left skewed, and another one is zero skewness that you can call that as normal distribution or zero symmetrical. So we will talk about in a positively skewed distribution, the tail on the right hand side. The tail on the right hand side, the larger values is longer or fatter than the left hand side. The smaller values, this means that the most of the data points are concentrated on the left side of the distribution. This means that the most of the data points are concentrated on the left side of the distribution, and there are relatively few very large values on the right side. Example, income distribution in a population where most people have low to moderate incomes, but a few individuals have very high incomes. Then there comes negative skewness. Left skewed, you can call it as a left skewed. In a negatively skewed distribution, the tail on the left hand side, the smaller values is longer or fatter than the right hand side, the larger values. This indicates that most of the data points are concentrated on the right side of the distribution, and there are relatively few very small values on the left side. For example, exam scores of a relatively easy test where most students score high but a few students score very low. And then there comes zero skewness, symmetrical. A distribution is considered to have zero skewness when it's perfectly symmetrical, with equal tail lengths on both sides. The mean, median, and mode of a symmetrical distribution are all the same. Example, a standard normal distribution bell-shaped curve has zero skewness. You can calculate skewness using statistical functions or libraries in Python, such as scipy stats.skew or the skew methods in pandas. Skewness is useful in data analysis because it can influence the choice of data preprocessing techniques and selection of appropriate statistical models. It is often important to address skewness, especially in machine learning, as some algorithms assume normally distributed data or perform better with less skewed data. Now we will want to know that how the distribution affects the results of a model. So skewed data can introduce several issues when building and interpreting statistical and machine learning models. Understanding these issues is essential for data analysts and data scientists. So first issue that arises due to distribution is biased estimates. Skewed data can lead to biased estimates of statistical parameters. For example, the mean may be pulled towards the skewness, causing it to be unrepresentative of the central tendency of the data. In contrast, the medial value is less affected by skewness and often provides a better measure of the central tendency for skewed distribution. And then another one comes model assumption. Many statistical models assume that data follows a normal distribution. Skewed data violates this assumption, potentially leading to incorrect inferences and predictions. Linear regression, for example, assumes normally distributed residuals, and skewness in the data can result in non-normally distributed residuals. Then another one comes inferior model performance. Skewed data can negatively impact the performance of a machine learning model. Models like linear regression, logistic regression, and k-means clustering may not work optimally with skewed data because they rely on underlying assumptions that are not met. Skewed data can lead to inaccurate predictions and suboptimal model fits. Then comes loss of information. So extreme values in skewed data can be underrepresented, leading to a loss of information. These extreme values may contain valuable insights or outliers that could be important for decision making or anomaly detection. The next comes inaccurate, insignificant. In hypothesis testing and statistical significance analysis, skewness can lead to incorrect conclusions. P-values and confidence intervals may be biased, potentially leading to type 1 or type 2 errors. And next comes challenges in visualization. Skewed data can make it challenging to visualize the data effectively. Traditional histograms may not reveal the true underlying patterns, and it might be necessary to transform the data or use alternative visualization techniques. Difficulty in interpreting coefficients. In linear models, the coefficients of features can be challenging to interpret when the data is skewed. This can make it harder to understand the impact of individual features on the target variable. To address these issues, it is often necessary to pre-process skewed data. Common approaches include transformation applying mathematical transformations like log, square root, cube root, or box-Cox transformations to make the data more symmetric. And another method comes is binning or categorization. Converting continuous data into categorical bins can help reduce the impact of extreme values. Then comes outlier handling. Identifying and handling outliers can mitigate their influence on skewed data. Another one is choosing appropriate models. When dealing with skewed data, consider using models that are less sensitive to distribution assumptions, such as decision trees, random forest, or robust regression methods. Ultimately, the choice of approach depends on the specific characteristics of your data and the goals of your analysis or modeling task. It is essential to evaluate the impact of skewness on your results and choose the most appropriate techniques accordingly. Now, how can we handle the skewed data? Handling data with skewness is an important step in data pre-processing, as skewed data can negatively impact the performance of many machine learning algorithms. Skewness refers to asymmetry in the distribution of data points. There are several methods to handle skewed data depending on the nature of the skewness and the specific problem you are working on. Here are some common techniques to handle skewed data. Log transformation. You can use logarithm function to transform positively skewed data, write skewed data into a more normal distribution. This is particularly effective for the data with exponential or multiplicative skewness. For data with zero or negative values, consider adding a constant to the data before applying the log transformation to avoid. For data with zero or negative values, consider adding a constant. For data with zero or negative values, consider adding a constant to the data before applying the log transformation to avoid issues with undefined values. The next one comes square root transformation. The square root transformation can be used for moderately right skewed data to reduce the skewness and make the data more symmetric. The next one comes box-Cox transformation. The box-Cox transformation is a more generalized power transformation that can handle both right and left skewed data. It tries to find the best power transformation to make the data as close to a normal distribution as possible. Then comes Johansson transformation. Similar to the box-Cox transformation, the Johansson transformation is another option for handling both positive and negative skewness. It can be implemented using Johansson function from the SciPy library. Another one comes data removal. In extreme cases, you might consider removing extreme outliers or data points that are causing the skewness. However, this should be done carefully and with a good understanding of the data and domain. So, each transformation aims to reduce the skewness of the data. The choice of transformation depends on the specific characteristics of your data and assumption of your modeling technique. After applying these transformations, you can check the skewness of the transformed data to assess how well each method worked in reducing skewness. And till now, if you are watching this video, please do not forget to subscribe and like the video.